Imagine you are standing on the Thames in January 1684. Not beside it, on it. The river is frozen solid, not a skim of ice, not a crust you'd avoid, but a compacted mass thick enough that an elephant could walk across it without cracking the surface. And people are, not elephants, but people, thousands of them, running a market on the frozen river, with stalls selling hot food and printed souvenirs, and reportedly, in one documented instance, a whole ox being roasted directly on the ice above what should have been the flow of one of England's major waterways. This was a frost fair. And it was not a one-off curiosity. The Thames froze significantly at least 24 times between the 14th and 19th centuries, during the period historians now call the Little Ice Age and the absolute coldest. Most sustained cluster of those freezes happened between 1645 and 1715. Here is the question the story opens with, and the one it will spend considerable time closing. Why? Not why did it freeze. The mechanism of freezing is not mysterious. Why that period specifically? Why that intensity? Why 70 years of conditions so reliably brutal that the river at the center of the largest city in the Western world regularly became a street fair? The answer involves the sun, a 70-year silence, 2 Victorian astronomers, a credential dispute, and a woman whose name does not appear in the things she helped discover. Let's start at the beginning, because the beginning requires understanding what sunspots actually are and why their absence matters. The sun is not a stable, uniform object. It is a churning plasma furnace with an extraordinarily complex magnetic field that varies on roughly 11-year cycles. During periods of high solar activity, its surface is dotted with sunspots, dark regions where intense magnetic fields suppress the convection of hot plasma, making those areas slightly cooler and darker than their surroundings. Sunspots are paradoxically associated with a more active, energetic sun. More spots means more solar radiation across the electromagnetic spectrum, including the ultraviolet radiation that interacts with Earth's atmosphere and, through a chain of mechanisms still being refined by modern climatology, affects surface temperatures. Fewer sunspots means a quieter sun. A quieter sun means slightly less energy reaching Earth. Slightly less energy, sustained over decades, means a measurably colder planet. Between 1645 and 1715, the sun went quiet on a scale that has not been repeated in the centuries since. This is the Maunder Minimum, named, eventually, by scientists who came long after it ended, for reasons we'll get to, in a naming convention that turns out to be its own minor historical crime. During the 28-year window of 1672 to 1699, observers across Europe recorded fewer than 50 sunspots. 50. In the modern era, the sun produces 40,000 to 50,000 sunspots in a similar span. The drop is not a rounding error. It is not a measurement quirk. The sun, during this period, had essentially gone dark on its surface, and the consequences were being felt on the ground by millions of people who had no idea their primary heat source had entered an extended hibernation. Go back to 1645 then, the year the minimum begins. England in 1645 was in the middle of its civil war, which, given what was happening cosmically, feels appropriate. Parliament and the royalist forces of King Charles I were grinding through the final stages of a conflict that would end with the king's public execution 4 years later. The country was militarily, economically, and psychologically depleted. The harvest failures that had been accumulating across the previous decades, part of the Little Ice Age's slow tightening grip, had already made food scarcer and more expensive. And now, entering a period of solar quiet that would deepen over the coming decades, the cold was going to get worse. Nobody knew. This is the part that takes a moment to absorb. The Maunder Minimum did not announce itself. There was no contemporaneous recognition that the sun was behaving unusually, because there was no sufficient baseline of observation to recognize the anomaly. Galileo had begun systematic sunspot observation in the early 1600s. Other astronomers across Europe and Germany, in France, in England had made their own records. But those records were not yet a coherent data set. They were individual scientific observations scattered across institutions that did not routinely share data. When the sunspots became sparse in the late 1640, and then nearly vanished in the following decades, the astronomers who noticed simply noted fewer sunspots in their logs and moved on. There was no alarm. There was no paper. There was just the quiet accumulation of entries that said, essentially, nothing to observe today. Meanwhile, on the ground, people were dying of cold. Not dramatically, not all at once, but in the grinding cumulative way that cold kills, through failed harvests, through livestock that couldn't survive the winter, through the energy cost of simply staying warm enough to function when wood was expensive and drafty buildings were the standard. Europe in the second half of the 17th century experienced some of the worst famine conditions in recorded history. The 1690s in particular were a decade of catastrophic agricultural failure across Scotland, Scandinavia, France, and Central Europe. France lost perhaps a tenth of its population to starvation during the famine of 1693 to 1694. Scotland's agricultural economy came close to collapse. None of this was understood as solar. None of it could have been, with the information available. The connection between solar activity and terrestrial climate is not obvious. It requires a data chain running from telescope observations through atmospheric physics through agricultural records. And the 17th century had fragments of that chain, not the whole thing. People blamed weather, blamed God, blamed poor governance, blamed each other. The actual cause was 93 million miles away and temporarily not producing the magnetic activity that helped regulate the energy balance of their world. The minimum continued. The Thames froze in the winter of 1663, again in 1666, severely in 1677, catastrophically in 1684, and again in 1695. Each freeze was a public event. The frost fairs that Londoners organized on the ice were acts of collective, almost defiant adaptation to the cold. You can read the records. The printing presses hauled onto the ice to produce novelty newspapers, the puppet shows, the skating, the bonfires. The absolute refusal of English urban culture to acknowledge that the river, being a solid platform rather than a liquid one, was anything other than an opportunity for commerce and recreation. It is, in its way, admirable. It is also a very specific kind of gallows humor, dressing up the symptom of a climate crisis as a festival. Isaac Newton was doing his foundational work on optics and gravity during this period. Christopher Wren was rebuilding London after the Great Fire of 1666 in a colder city than the one that had burned. John Flamsteed, appointed as the first Astronomer Royal in 1675, was establishing the Greenwich Observatory that would become one of the most important astronomical institutions in history during the deepest, darkest stretch of the Maunder Minimum, looking up at a sun that was telling him, in the language of missing sunspots, that something was wrong. He didn't have enough historical data to hear it. The minimum began to ease in the early 1700s. By 1715, sunspot activity was returning towards something closer to historical norms. The Little Ice Age continued. It would persist, in attenuated form, for more than a century after the minimum ended, but the most acute phase of solar quiet was over. And then, the event disappeared from scientific consciousness for 170 years. This is the part that requires a moment of genuine bewilderment. A 70-year period of anomalous solar behavior, embedded in the historical astronomical record across multiple European observatories, coinciding with one of the most sustained cold periods in the last 1,000 years. And it sat there, in the logs, unnamed and unrecognized, for a century and 3/4 after it ended. The reason is one of the quieter catastrophes in the history of science. Nobody systematically looked. The records existed. The telescopic observations from the 1650s, 1660s, 1670s, 1680s were sitting in institutional archives. The data was there, waiting for someone to compile it, analyze it, and say, "Look at this gap. Look at how long the sun went quiet. This has never happened in the period of recorded observation." Nobody said it for 170 years because scientific fashion had moved on. Solar observation had become routine rather than urgent, and the connection between solar activity and terrestrial climate was not yet a question that anyone had framed precisely enough to demand an answer. Enter Gustav Spörer. Spörer was a German astronomer working in the latter half of the 19th century, and his particular obsession was sunspot behavior over historical time. He went into the archives. He went through the old records systematically, methodically, the way that a particular kind of scientist goes through historical data when they suspect the data contains something no one else has noticed. And he found it, the gap, the 70-year near absence of sunspots between 1645 and 1715. He published his findings in 1887. Then again, in 1889, they were relayed to the Royal Astronomical Society in London, and they were, for the most part, ignored. Gustav Spörer spent years documenting one of the most significant solar anomalies in recorded history, and the response from the broader scientific community was, essentially, a polite nod and a change of subject. The idea that the sun could behave so differently for such an extended period that solar activity was not a stable background constant, but a variable that could drop to near zero for 7 decades, was not yet a comfortable fit with the models of solar behavior that 19th century astronomy had constructed. Then Edward Maunder read Spörer's work. Edward Walter Maunder was born in 1851 in London and had spent his career as a solar observer at the Greenwich Observatory, the same institution Flamsteed had established during the minimum itself. Maunder's professional focus was sunspots, their distribution, their movement, their relationship to the solar magnetic cycle. When he encountered Spörer's historical analysis, he recognized immediately what it was and what it meant. In 1890, Maunder published a paper citing Spörer's work and drawing attention to the prolonged sunspot minimum. In 1894, he published again. Maunder had access that Spörer lacked: the Royal Astronomical Society's imprimatur, the Greenwich Observatory's prestige, and the English language, which in the late Victorian era was increasingly the dominant tongue of international scientific publication. His papers reached a wider audience. His framing of the issue, the prolonged sunspot minimum, gave the phenomenon a handle that scientists could grasp and debate. The scientific community still didn't entirely buy it. The notion that the historical record was complete enough to confidently assert a 70-year absence of sunspots was contested. Some argued the gap in the record reflected gaps in observation rather than actual solar behavior. It was a legitimate methodological debate, and it would not be conclusively resolved until the 20th century, when physicist John Eddy published a comprehensive 1976 analysis using additional proxies. including carbon-14 records from tree rings. That confirmed the minimum was real and not a data artifact. The period was named in that 1976 paper, the Maunder Minimum. Now, about Annie Russell Maunder. Annie Russell was born in 1868 in County Down, Ireland. She was a mathematician, a genuinely exceptional one, trained at Girton College, Cambridge, where she completed the mathematical tripos examinations. Cambridge in the 1880 awarded women who completed the tripos their equivalent scores but not their degrees, not formal degrees. The degree went to men. Women received a certificate of completion and the knowledge that they had demonstrated intellectual equivalence to their male counterparts, which the institution then declined to officially recognize. She went to work at the Greenwich Observatory in 1891 as a lady computer, the term used for the women hired to perform the mathematical calculations that the observatory's scientific work required. The pay was lower than her male colleagues, the institutional status was lower, and the formal credential she hadn't been permitted to receive meant that her work could be published, but not, officially, in her own name. She met Edward Maunder at Greenwich. They married in 1895. And Annie Russell Maunder proceeded to do substantial scientific work on exactly the solar phenomena her husband was investigating. She worked on sunspot analysis. She contributed to the photographic and analytical methods the observatory was using to track solar activity. She co-authored papers with her husband. Some of the analytical foundations of what became the accepted understanding of the Maunder Minimum bear the marks of her mathematical contributions that, because she had no university degree, could not be publicly credited to her under the institutional rules of the time. Let's sit with that for a moment. The Maunder Minimum, this 70-year solar event, this cosmic explanation for the frozen Thames and the failed harvests, and the ox on the ice, is named after Edward Maunder. Spörer, who found the gap first, gets a separate entry. There's a Spörer minimum and a Spörer's law, which is some consolation. But Annie Russell Maunder, who worked alongside her husband on this material, who had the mathematical training that in any other institutional context would have made her a credentialed scientist in her own right, does not appear in the name. She was not written out through malice exactly. She was written out by a system that gave Cambridge mathematics degrees to men, certificates to women, and then used the absence of the degree as justification for not attaching her name to the work the degree would have sanctioned. It's a neat circle of exclusion. Deny the credential, then use the absence of the credential as grounds for the denial of recognition. Annie Russell Maunder continued working. She became one of the founding members of the British Astronomical Association, an organization specifically established to be open to women at a time when the Royal Astronomical Society was not. She published papers. She made contributions to solar photography. She was recognized by her peers, quietly and informally, as a scientist of real ability. She died in 1947. Having lived to see the Royal Astronomical Society finally admit women as fellows in 1916. The minimum she helped document retained its name. Now let's return to the event itself and ask the question that climate scientists have been arguing about ever since John Eddy's 1976 paper gave it a name. Did the Maunder Minimum actually cause the Little Ice Age? The honest answer is, probably not by itself and definitely not entirely. The Little Ice Age began well before 1645. Its origins trace back to the 13th and 14th centuries, to a period of volcanic activity that injected sulfur into the stratosphere, reflecting sunlight and initiating a cooling that then fed back into itself, as expanding ice sheets reflected more solar energy. By the time the Maunder Minimum began, The Little Ice Age had already been running for 300 years. What the minimum appears to have done is intensify it. The reduced solar output during this period, a reduction estimated by modern solar physicists at roughly 1 to 2% below current levels, was small in absolute terms, but climate systems are not linear. Small, sustained inputs, compounded over decades, can push systems across thresholds. The coldest decades of the Little Ice Age coincide with the deepest decades of the Maunder Minimum, with a precision that statistical analysis finds difficult to attribute to chance. The causal relationship remains an active area of scientific research and some debate. Climate modelers working with paleoclimate data generally accept that the minimum contributed to cooling, but disagree on the magnitude of its contribution relative to volcanic forcing, ocean circulation changes, and other factors. What is not disputed is the correlation. The period of near-total solar quiet and the period of maximum cold are essentially the same period, with the same start and end points, and the people living through both experience them as one continuous catastrophe. Consider what those people knew. A farmer in Oxfordshire in 1680 knew that the winters had been getting harder. He knew that the spring came later and left sooner than it had in his father's memory. He knew that the price of grain had been climbing, that livestock were thinner going into each winter, that the village he'd grown up in had lost people to cold, to hunger, to the diseases that follow malnutrition. He had no framework for any of it. He had no concept of sunspots, no telescope, no access to the sparse astronomical records that would eventually reveal the solar silence happening above his head. He was living inside the consequence of something he could not name, caused by something he could not see, that would not be understood until 200 years after his death. This is, when you follow the thread all the way out, what the Maunder Minimum actually is. Not just a solar anomaly, not just a data point in the Little Ice Age. It's a story about the gap between what happens to people and what those people are able to understand about why it's happening. The sun went quiet. The world got cold. People froze and starved and held frost fairs on rivers that should have been flowing. None of them could have told you why. The answer took 242 years to arrive. It arrived in pieces. Spörer's archival work in the 1880, Maunders' papers in 1890 and 1894, the contested debates of the early 20th century, Eddy's definitive analysis in 1976. And layered across that entire arc of discovery was the contribution of a woman who did some of the mathematical work, co-authored some of the analysis, and received in return the institutional acknowledgement that she did not have the right piece of paper. The Maunder Minimum. 70 years, nearly silent. Fewer than 50 sunspots in 28 years, against a modern baseline of 40 to 50,000. The Thames frozen hard enough for printing presses. Harvests failing across a continent whose farmers had no language for what was happening to them. An astronomical record sitting in archives for a century and a half, waiting for someone to read it carefully enough. A German astronomer who read it and was mostly ignored. An English astronomer who amplified it and got his name on it. And a mathematician who helped with the analysis and did not get her name on anything. Modern astronomy has, at least, given Annie Russell Maunder some retroactive recognition. There is a crater on the moon named for her. There is a medal given by the Royal Astronomical Society bearing both their names, the Eddington Medal's poor cousin, a later addition to the institution's recognition of her. The period is still called the Maunder Minimum. One final thing worth noting, because it would be dishonest not to. The Maunder Minimum is now, in the 21st century, a term that appears regularly in popular science coverage, usually in the context of speculation about whether a new solar minimum is approaching, and whether it might offset global warming. The short answer from climate scientists is no. The solar forcing from a new Maunder scale minimum would be, in modern estimates, sufficient to reduce global temperatures by perhaps 0.3 degrees Celsius over several decades against a background of anthropogenic warming that is already pushing 1.5 degrees and climbing. The sun going quiet again would not save us. It would be a wet cloth on a house fire. Which means the Maunder Minimum is doing double duty in the historical record. It is simultaneously an example of natural climate forcing that had catastrophic effects on human populations effects that took centuries to explain, and a cautionary data point for anyone who imagines the next solar cycle will ride to the rescue of a warming planet. The sun went quiet for 70 years. The world froze. Nobody understood it at the time. When someone finally explained it, she didn't get her name on it. And the sun, in its own good time, started producing sunspots again, as if nothing had happened. It does not care what we name the silence.